Tonight, the James Webb Space Telescope looks back so far that the universe barely has time to become itself. And what it seems to show is unsettling. Galaxies appear bright, structured, and busy with stars at a time when, on paper, there should barely be enough time for them to exist at all. The timeline does not add up. Or maybe it is our expectations that do not add up. If you like these calm, sleepy journeys through the real mysteries of space, you can subscribe and drift with us again on another night. Now let's lower the lights, soften the edges of the day, and follow the oldest light we can reach. Imagine you are outside the Earth, far above the weather, where the planet's noise fades into a gentle glow. There is no wind, no birds, no engines, only the slow turning of blue and cloud beneath you. Above you, the sky is not a dome, it is a depth. Stars are not pinned to a ceiling, they are holes in distance. And somewhere out there, so far that your mind cannot naturally hold it, there are the first galaxies. They are not far in the way a mountain is far. They are far in time. Their light leaves when the universe is young, when atoms are still settling, when the first generations of stars are learning how to shine. That light travels for more than 13 billion years, not as a beam you can point to, but as a widening shell, spreading through the expanding cosmos, thinning and reddening as it goes. And then, on one quiet day in our century, it touches a mirror made by human hands. To understand why this feels like the timeline breaks, we first need to understand what looking back actually means in space. In everyday life, seeing is immediate. In the universe, seeing is memory. Light takes time. So every telescope is a time machine, not because it moves, but because it waits. The James Webb Space Telescope waits in a particular way. It does not look for visible light like your eyes do. It looks for infrared, the kind of light that feels like warmth. And this matters because the oldest light gets stretched by the expansion of the universe. The more it travels, the more the wavelengths stretch, sliding from ultraviolet into visible, then into infrared. Webb is built to catch that stretched light, like catching a whisper that has been carried across a vast hallway. But there is a catch. When you catch a whisper, you still have to interpret what you heard. And in the early days of Webb's discoveries, interpretation is where the drama begins. A gentle companion joins us here, like a quiet voice in a planetarium after everyone else has gone home. When you say the timeline does not add up, do you mean the universe is wrong, or your calculations are? That is the right question, because the universe is usually not wrong. But our models are stories we tell with math, and stories can be incomplete. So let's set our central questions softly on the table between us. When Webb looks back toward the first galaxies, why do some of them seem too bright, too massive, or too mature for their age? And what could explain that without breaking everything we think we know? We make a few promises as we go. First, we keep returning to one image, a single ancient photon, because the entire mystery rests on tiny packets of light and what they carry. Second, we keep returning to a limit, the horizon of certainty, because the farther back we look, the more our confidence thins. Third, we repeat a small phrase, like a lullaby for the skeptical mind. The light is honest, but our reading can be wrong. Now we begin with the simplest mental model, one you can hold even as you get sleepy. The universe begins with a hot, dense, early state. It expands and cools. After a few 100,000 years, atoms form and light can travel freely. Much later, the first stars ignite. Then the first galaxies assemble, not as finished cities, but as scattered lights gathering into neighborhoods. Over time, small structures merge into larger ones. That is the broad expectation in standard cosmology, a slow climb from simple to complex. So when Webb shows us very early galaxies that look surprisingly bright and abundant, it feels like finding a mature forest in a place where you expect only seedlings. And this is where it gets strange. Some of the earliest Webb images and surveys reveal candidates that appear to sit at extremely high redshift, meaning their light has been stretched a lot, implying they are very far back in time. Some of these candidates appear unexpectedly luminous. In early interpretations, that luminosity translates into large stellar masses, which implies rapid growth, which pushes against many pre-Webb expectations. But before we let that become a crisis, we need to understand how astronomers estimate distance and age for these faint smudges. There are two main approaches. One is photometric, based on colors across filters. The other is spectroscopic, based on identifying specific lines in the spectrum. Photometric redshifts are like guessing a song from a few notes. You measure the brightness in multiple filters, and you look for a sharp drop, a break, where the galaxy becomes dim in bluer filters because the light has been absorbed by hydrogen along the way. That break slides to redder wavelengths the farther back the galaxy is. It is clever, and it works well, but it can be fooled. Spectroscopic redshifts are like hearing the full melody. You spread the light out and look for emission lines, fingerprints from atoms. If you can identify the lines, you can measure redshift more directly. It is slower, harder, and requires brighter targets or longer observing time, but it is more definitive when it works. So the first wave of impossible galaxies might be guesses from partial notes. Exactly. And there is no shame in that. It is how discovery begins. You see something odd, you flag it, then you test it. Now, picture a deep field image. It looks like a sprinkle of glitter on black velvet. Each speck is a galaxy, often containing billions of stars. Each star, a sun. Some specks are small and red, barely there. Those are the ones that pull your attention, because red is often the color of great distance in Webb's world. But red can also mean other things. Dust can redden light. Old stars can redden light. Certain emission lines can make an object appear bright in one filter and dim in another, mimicking a break. So the early days of Webb are filled with a kind of cosmic detective work. Every candidate is a question. Is this truly a galaxy from cosmic dawn? Or is it something closer, wearing a disguise? This is the horizon of certainty. We can see astonishingly far, but we cannot see with perfect clarity. And the universe is full of lookalikes. Now we begin to feel why the timeline does not add up. Because if you take the most extreme interpretation at face value, you get galaxies that appear too massive too soon. That would imply either that star formation is far more efficient at the dawn of time than we thought, or that our understanding of early structure formation needs adjustment, or that we are misreading the light. And the calm truth is that all three can be partly true at once. So let's walk slowly through the main reasons the timeline can look broken, starting with the most human one: mistaken identity. One common issue is that a lower redshift galaxy with lots of dust can look like a higher redshift galaxy because dust absorbs blue light and makes the object red. Another issue is that some galaxies have strong emission lines. Those lines can boost the brightness in certain filters, tricking the photometric redshift estimation. There are also cool stars in our own galaxy that can masquerade as distant galaxies in color space, though careful analysis usually weeds those out. Which brings us to a quiet but important idea. Webb is so sensitive that it sees things that older telescopes barely hinted at. That means we are exploring new territory in data interpretation, and the maps are still being drawn. Now, let's talk about brightness and mass, because this is where the too big too soon feeling often comes from. When you see a galaxy, you see its light. To estimate its stellar mass, you model the kinds of stars that would produce that light, their ages, their metallicities, and how dust might dim them. You are essentially translating a glow into a population. But that translation depends on assumptions. If you assume the light is mostly from stars, you infer a certain mass. If some of the light is actually from an active black hole, or from intense nebular emission, the inferred stellar mass can drop dramatically. And this is where Webb introduces a new kind of mischief. In the early universe, many objects are compact and bright in ways that can be powered by accreting black holes or extreme star formation, not just by serene populations of stars. If you mistake one for the other, the timeline looks wrong. Archivist: you are saying the crisis might be an accounting error, not new physics. It might be. And in fact, some follow-up work suggests that at least part of the early, impossibly massive story softens once you account for these effects, and once better data arrives. Some analyses find that early mass estimates can be inflated, and that when corrected, the galaxies fit more comfortably within expectations, though the early universe still looks impressively productive. So the timeline may not be broken, but it may be more lively than we anticipated. Now we take a small detour, a breathing moment. Imagine the early universe like a dark room filling with candles one by one. The first stars ignite, small at first, then more. The room is not evenly lit. Some corners flare early, some stay dim longer. The first galaxies are not a uniform first. They are a patchwork of early bloomers and late bloomers. That patchwork matters because Webb's deep fields do not sample the entire universe. They sample narrow pencil beams through space. And in a patchy cosmos, a pencil beam can hit a surprisingly active neighborhood by chance. This is cosmic variance, a quiet phrase that can feel like cheating, but it is real. You might look into one region and see an overabundance of bright, early candidates. Look into another and see fewer. Early results can be biased by where you happened to look. So the timeline may not add up globally. It may look that way in a particular slice. Now we return to the photon, our recurring object. A single photon leaves a young galaxy. It carries information about the stars that emitted it, about the gas it passed through, about the intergalactic medium that absorbed certain wavelengths. It travels. The universe expands.
The photon stretches. Then it arrives at Webb. It hits the mirror, bounces, and gets measured as a number in a detector. That number becomes a pixel, then a
point in a catalog, and a paper. Then a headline that says the universe is broken. But the number itself is just honest light. The rest is interpretation. And this is where it gets strange again. Webb does not just show early galaxies. It shows early galaxies that look different than we expected. Some are compact and red. Some show strong lines. Some seem to host growing black holes at ages that feel uncomfortably early. The early universe is not a quiet nursery. It is a workshop. One of the most surprising populations discussed in recent years is a class of compact, very red objects nicknamed little red dots. Their exact nature is still debated. Some interpretations suggest they could be galaxies with active black holes contributing strongly to their light, which would change how we estimate their stellar masses and ages. Other models propose alternative explanations for their appearance. Either way, these objects are part of the broader theme. Early light can mislead you if you assume it comes from ordinary stars alone. Archivist. So the universe might be loud, but in a language you are still learning. Yes. And learning a language always begins with misunderstanding. Now, let's turn toward the first Galaxies phrase in the title, because it carries its own subtle problem. First can mean earliest in time, or first in a particular observational window, or first that we can confirm. Webb keeps pushing records, but record setting is not the same as understanding. There are candidate galaxies suggested at extremely high redshift, and there are spectroscopically confirmed galaxies at very high redshift as well. The confirmed ones anchor our timeline. They tell us, yes, galaxies exist when the universe is only a few 100 million years old. That alone is astonishing, but it is not impossible. Structure formation does begin early. The question is how quickly some galaxies become luminous and what that luminosity truly represents. Now, to understand why brightness is such a big deal, we need to remember that in the early universe, everything is compressed in time. 100 million years is long on human scales, but short in cosmic assembly terms. If a galaxy looks like it has formed billions of solar masses of stars very quickly, it challenges star formation models, feedback, and the way gas cools and collapses into halos. So one way the timeline could not add up is if star formation is more efficient earlier than predicted. But there is a catch. Efficiency can be boosted by things we already expect in the early universe. Gas is more abundant. Halos are assembling rapidly. Mergers are common. There may be fewer heavy elements, which changes cooling and radiation. Star formation can occur in intense bursts. A galaxy can be bright not because it is massive overall, but because it is caught during a surge. That is a key idea. Webb may be catching the universe in its most dramatic moments, not its average mood. And there is another quiet factor. When we say massive, we often mean stellar mass. But early galaxies might have different stellar populations. If early stars are, on average, more massive and hotter, they produce more light per unit mass. That means a bright galaxy might not require as much stellar mass as you would infer using later universe assumptions. This is an area where astrophysicists argue carefully,
because changing the initial mass function is not something you do lightly, but it is part of the landscape of possibilities. So you can make the same glow with fewer stars if the stars are different. Yes, and the early universe is where different is most plausible. Now we shift into another movement, one that helps the timeline feel less like a spreadsheet and more like a place. Imagine the cosmic dawn. The universe is filled with hydrogen gas, mostly neutral. Neutral hydrogen is good at absorbing certain wavelengths of light, especially ultraviolet. So even
If stars form, their light has to fight through fog. Over time, as galaxies produce energetic photons, they ionize the hydrogen around them, carving out bubbles of clearer space. Eventually, these bubbles grow and merge, and the universe becomes more transparent. This transition is called reionization. Reionization is not just a chapter heading. It is a story of the first galaxies changing the very medium they live in. And Webb is now seeing hints that this story may begin earlier or be patchier than we once thought. One striking signpost is the detection of Lyman alpha emission from a galaxy at extremely high redshift. Lyman alpha is a line that is usually suppressed in the very early universe because neutral hydrogen absorbs it. So seeing it bright and clear at such an early time suggests that the region around the galaxy is more ionized than you might expect, or that the galaxy's line is produced and transmitted under special conditions. This does not break cosmology. It reveals complexity. It says the early universe is not uniformly foggy. There are holes, there are bubbles, there are clearings. And if there are clearings, galaxies in those clearings can look surprisingly bright and mature, not because they are older, but because their light escapes more easily. Archivist. So the timeline might look wrong because you assume the fog is the same everywhere. Exactly. Reionization is not a curtain that lifts all at once. It is more like dawn in a landscape with hills and valleys, where light touches some places sooner than others. Now, let's talk about another reason the timeline can feel off: gravitational lensing. Mass bends space. A massive cluster of galaxies between us and a distant galaxy can act like a lens, magnifying the background object. This can make a distant galaxy appear brighter than it intrinsically is. Lensing is both a gift and a complication. It lets us see fainter objects, but it also means you must carefully correct for magnification, and those corrections can be uncertain. If you underestimate lensing, you overestimate a galaxy's brightness, and therefore its mass. That again makes the timeline look broken. So the early universe, as seen by Webb, is a place where many effects stack. Dust, emission lines, black holes, bursty star formation, lensing, patchy reionization, and selection bias. Any one of these can tilt interpretation. Together, they can make a young galaxy look like an ancient one. And this is why the story is so compelling. The timeline doesn't add up is not only a headline, it is a genuine scientific tension that forces the field to refine tools, improve models, and test assumptions. Now we pause again, a soft pause. Imagine you are holding a page of faint handwriting. The ink has faded. Some words are smeared. Some lines are missing. You are asked to reconstruct the meaning. You do your best, and you make a guess. Then someone finds a clearer copy of one paragraph and realizes your guess was off. That is how early astronomy often works, not because people are careless, but because the data is hard. Now we continue, and we move from why it looks wrong to what we are learning. One of the biggest lessons of Webb's early years is that the cosmic dawn contains more luminous objects than many people expected, and that some of the earliest candidates are real, but their properties are still being pinned down. Follow-up studies increasingly show that some early claims of extreme stellar masses can be reduced when you account for line contamination and the possibility that some sources are powered partly by black hole accretion rather than purely by starlight. That does not erase the wonder. It shapes it into something more accurate. The timeline might not be broken, but the pace of early growth might still be faster, or at least more efficient in certain environments, than the median pre-Webb simulation suggested. And that leads to a deeper kind of excitement. Because if the early universe can build bright galaxies quickly, it tells us something about the physics of gas cooling, star formation, feedback, and black hole growth under primordial conditions. Archivist, is this the part where you discover your model has missing ingredients? Yes. And missing ingredients are not failures. They are invitations. Now, let's gently examine one of those ingredients: feedback. When stars form, they do not just sit quietly. Massive stars emit intense radiation. They explode as supernovae. They heat and stir the gas. This feedback can regulate star formation by blowing gas out or preventing it from collapsing further. Many models assume feedback is strong enough to limit early growth, but in the earliest galaxies, the balance of feedback might be different. Gas inflow might be so strong that even with feedback, star formation continues in bursts. Or the geometry might let outflows escape without shutting down the core. Or the interstellar medium might be structured differently. So the timeline tension could be telling us that early feedback works differently, or that the inflow of gas into halos at cosmic dawn is more efficient, or that star formation in dense, early environments reaches higher peaks. Now, let's bring in black holes again, because they are often the hidden variable. A black hole that is actively accreting can outshine the stars and its host in certain wavelengths. In the early universe, if black holes grow quickly, they can make galaxies appear brighter and redder. And if you attribute that light to stars, you overestimate stellar mass. Some early compact red sources may involve this phenomenon, and the community is actively debating what fraction of early luminous sources are star-dominated versus black hole-dominated. This matters because it changes the narrative. Instead of "galaxies are too massive too soon," the story could become "black holes are shining early, making some galaxies look more massive than they are." That is still a profound puzzle, because black holes growing fast is itself a puzzle, but it shifts which timeline is stressed. So, the timeline problem might not be galaxies. It might be black holes. It might be both, intertwined, like two vines on the same trellis. Now we step into another calm image. Think of a newborn city at night. Some buildings are finished, some are half-built, some streets are lit, others are dark. If you fly overhead and see a bright cluster of lights, you might assume the whole city is mature. But brightness can be concentrated. It can be local. It can be temporary. Cosmic dawn is like that. Webb sees clusters of light in deep fields. Those clusters might be the brightest neighborhoods of early structure, not representative of everything.
And because Webb is so sensitive, it finds the brightest anomalies first. This is another quiet selection effect. When you push into a new regime, your first
Discoveries are often the most extreme. So as time passes and surveys deepen and widen, the population statistics become clearer. Some of the most extreme early interpretations soften. Others remain intriguing. Some candidates are confirmed at very high redshift, anchoring the fact that galaxies and even luminous systems exist astonishingly early. But the question of how common they are and what their true masses are evolves as the data improves. This is how the timeline slowly becomes consistent, not by ignoring tension, but by refining it. Now we take a gentle turn toward the phrase, "timeline doesn't add up," and ask what it really means in science. It does not mean throw away cosmology. It rarely means that. It means there is a mismatch between observation and expectation. And mismatches are where science lives. They are where you check your measurement pipelines, your selection functions, your assumptions about dust, your templates for stellar populations, your priors about what is common and what is rare. Sometimes the mismatch disappears as you correct a bias. Sometimes it persists and demands new physics. Most often, it turns into a more nuanced understanding, where both the observation and the model are partly right, and both need adjustment. The Webb early galaxy story feels like it is moving toward that nuanced place. The universe still looks young and surprising, but it might not be impossible. Now, let's revisit the earliest confirmed objects and what they imply, but we do it carefully. There are galaxies confirmed at redshifts around 13 and beyond, meaning their light comes from when the universe is only a few 100 million years old. Some appear very luminous, and at least some show spectral features that tell us about their gas and their ability to ionize the surroundings. These confirmations show that cosmic dawn is not a quiet period with a few tiny sparks. It is active. It has bright points that can carve bubbles in the fog. That alone can make the timeline feel faster than older intuition, but it is still compatible with a universe where structure begins early and where rare peaks in the density field collapse first, forming the earliest and brightest objects. So the timeline can add up if you remember that rare things happen first. Exactly. The first collapses happen in the rarest peaks, the places where density is slightly higher than average. Those become the first cradles of galaxies. Webb is very good at finding them. Now, another movement. We step into the concept of redshift itself, because it is easy to treat it as a number and forget it is a physical stretch. Imagine a slinky. If you shake it and a wave moves along it, and then you pull the slinky longer as the wave travels, the wave stretches. That is redshift. The universe expands, and light traveling through it stretches. The farther it travels, the more it stretches. So when Webb sees a galaxy that appears to be at very high redshift, it is not just far, it is long traveled. Its photons have been in flight since the universe is young. That is an astonishing thought on its own. But it also means that interpretation is fragile, because small errors in identifying breaks and lines can lead to large errors in inferred redshift. That is why spectroscopy is so important. It anchors the slinky stretch with identifiable markers. So one part of the Webb timeline story is simply the transition from photometric candidates to spectroscopic confirmations. The field is moving from possible to known in increments. And as it does, some early candidates move closer in redshift, some stay extreme, and the population distribution becomes clearer. This is not a scandal. It is science doing its slow work. Now, let's ask one of the deepest questions. Even if mass estimates come down for some sources, Webb still seems to suggest that the early universe is efficient at making light. Why? One answer is that early galaxies might be relatively dust-poor at the very earliest times, letting UV light escape more easily, making them appear brighter in certain bands. Another answer is that they might have intense bursts of star formation, producing many hot, massive stars that shine strongly in ultraviolet. Another is that the interstellar medium conditions produce strong nebular emission lines, which can boost certain photometric bands. And once you include these, you get a picture where early galaxies can be bright without needing to be impossibly massive. But the story does not end there. Because Webb is also teaching us that the early universe might be building black holes quickly, and that these black holes might be contributing to the light we see, even in systems that look compact and galaxy-like. So the timeline tension might be shared between two puzzles: the rapid appearance of luminous galaxies and the rapid growth of massive black holes. Those two may be linked. Gas that fuels star formation can also fuel accretion. Dense, early environments might nurture both. Archivist. So Webb is not breaking the timeline. It is revealing two clocks ticking faster than you expected. Yes, that is a beautiful way to frame it. Now, we begin to drift toward our payoff. But we take our time, because this is a sleepy channel, and we want the journey to feel continuous, like a river. Let's return to the horizon of certainty. The farther back you look, the smaller the sample sizes. The fainter the sources, the more you rely on complex models. That means extraordinary claims can appear early in a new dataset, simply because errors and biases are larger at the edge. Over time, as data improves, those claims settle into more stable shapes. This is exactly what begins to happen with Webb's earliest galaxy claims. Some early, massive galaxy results are revised when analysts include better treatment of emission lines, dust, and possible active nuclei. Some early, too many bright galaxies claims are tested against wider fields and improved selection functions. Some tensions remain interesting, but the most dramatic "everything is broken" tone often softens as the work continues. This is why, if you are watching science through headlines, it can feel chaotic. But through the quiet lens of process, it is steady. Now, the title says, "The First Galaxies," and that phrase pulls us into a final, gentle reflection. Even if Webb shows galaxies that are surprisingly bright early on, we are still looking at a stage after the very first stars. There is a deeper first behind the first. The first stars, sometimes called Population 3, formed from primordial hydrogen and helium. They may be massive and short-lived. We have not seen them directly yet. We infer their existence from theory and from the chemical fingerprints they would leave behind. The first galaxies may begin as small gatherings of those first stars. Then, Supernovae seed the environment with heavier elements. Gas chemistry changes, star formation changes, galaxies evolve. So when Webb looks back, it is peering into a transition, a universe moving from simple to complex, from pristine to enriched, from foggy to transparent. And in transitions, timelines often feel messy because multiple processes overlap. So the timeline does not add up because you are looking at a world mid-transformation. Yes, and transformation is rarely neat. Now, we return to our phrase one more time, and we let it land softly. The light is honest, but our reading can be wrong. Webb catches photons that have traveled since cosmic dawn. Those photons are real. But translating them into masses, ages, and histories requires assumptions. As our assumptions improve, the story becomes clearer. So what is the clearest story we can tell right now, without shouting? The first galaxies appear early, and some are remarkably luminous. Early observations suggest more bright candidates than many expected, though interpretation is complicated by dust, emission lines, black hole activity, lensing, and selection effects. Spectroscopy confirms that galaxies exist at very high redshift, anchoring cosmic dawn as a time of real structure, not just faint haze. Some early claims of impossibly massive galaxies soften with improved analysis, but the early universe still looks active, and black hole growth may be part of the surprise. In other words, the timeline is not a simple straight line. It is a braided stream, with fast channels and slow ones, with rare peaks collapsing early and lighting up the darkness before the average catches up. Now, we let the night return. You are here, in a warm room, on a planet orbiting a medium-sized star, in one arm of one galaxy. Above you, the universe has been expanding for billions of years, and a mirror far from Earth is collecting ancient light, photon by photon, building images that change what we think we know. If you'd like more calm journeys through the newest space mysteries, you can like and subscribe, and we'll meet again in the dark between the stars. And somewhere in that darkness, one ancient photon finishes its 13 billion year flight, touches a golden mirror, and becomes, for a moment, a tiny point of light behind your closed eyes.